Greeting, ladies and gentlemen. Today video I'm going to answering the tutorial 4. It is from my study, the first law of thermodynamic open system. So question number 5. Air flows steadily through a adiabatic turbine, entering at a 1 MPa, 500 degrees C and 120 meter per second, and leaving at a 150 kPa with the reduce in temperature 150 and 250 meter per second. The inlet area of the turbine is 18 centimeter square. Determine the mass flow rate of the air. That is equation. So it is mentioned the system were inadiabatic. So this means there is no heat loss all the way along the process. So this is the problem solving. We need to draw the schematic diagram for turbine, but it is not. I think that if you refer to textbook, it may differ to my diagram. It is because it just might differ, but point being is there is a inlet. The air were in upon the system with 1 MPa, 1 megapascal. Temperature that will be in degree C. Velocity 120, like I mentioned earlier. So there is the spec for the air at the outlet. So mass flow rate, since the system were in steady flow, so mass flow rate in equal to mass flow rate out. So it just depend on us. It is mean if you want to make an analysis at the inlet and outlet, it doesn't matter. You will get the same answer because it is a conservation of mass. So mass flow rate in equal to mass flow rate out. But in this case, I make an analysis in the inlet. Mass flow rate in equal to rho VA. It is also equal to specific volume, the power of -1, times by velocity and an area. So since that doesn't given what is the rho, the density for the air in the inlet, you need to find out. We can find out by the gas law equation, constant gas law equation, PV equal to RT. Since that we were dealing with the air, so the R gas constant will be 0.2870 K, refer to kilo. The temperature in the inlet will be 500 degrees C, but in this equation we need to use Kelvin, so you need to convert it into Kelvin. So that's why 773 over by the pressure at the inlet, the air in the inlet, there will be 1 megapascal. So we will get, if my math were right, 0.2219. So that is the specific volume in the unit of meter cube per kg. Now we can calculate the mass flow rate. Mass flow rate equal to 0.2219, the power of -1, times by 120. That will be the velocity of the air at the inlet, and times by the area that have been converted into meter, because remember we were dealing with a formula that in SI unit, so all must be SI unit. Centimeter square you need to convert into meter, so times by 80 times by 10, the power of 2, so we'll get 4.3263 kg per second. Question B asking the power output of the turbine. So there is my answer. I begin with an conservation of energy equation. Energy in, specific energy in equal to specific energy out. We can derive as a specific enthalpy plus by kinetic energy, potential energy. Work in is supposed to be work out, but I'm miss out a little bit, equal to H2 plus by KE2 plus by potential energy 2. Because there is no elevation upon the system, so we can deny the potential energy. Usually we deny the kinetic energy for turbine because the different in kinetic energy doesn't give much in submission of an energy. So that's why some people will neglect it, but for this equation I already included, so we will deal with an energy equation that have kinetic energy for turbine. So we tend to find out what is the work out is supposed to be worked out. We need to find the H2 and H1. H1 we can find by refer to A17 table of thermodynamic. You'll have a temperature in the form of Kelvin, enthalpy in the form of kilojoule per kg. From enthalpy, you can get the temperature. So enthalpy 2, you need to make enthalpy 1, you need to make an interpolation. Thus you will get something like 792.3825 kilojoule per kg. Doing the same thing for the enthalpy 2. Thus you will get 424.311 kilojoule per kg. You will rearrange the equation, thus you will get work in, and again it's supposed to be work out because turbine doesn't require work in, but it produces a work out that will generate an electricity. H2 minus H1 plus by kinetic 2, kinetic energy 2 minus by kinetic energy 1. In here, we were using the form of specific. The conventional formula for kinetic energy is half mv square. If we submission the unit of this formula, thus you will get joule. But in the form of specific, the m will cancel out. Thus you will get the kilojoule per kg. That is as same as the unit of enthalpy, because otherwise you cannot doing the algebra in submission. So H2, H1, you know, kinetic energy is half v square. The initial velocity for the air is 120, and the final will be 250. Thus we will get negative 344.0215 kilojoule per kg. The negative in here is indicate that the work in that I'm done in my calculation is supposed to be worked out. So this work in must be in here instead, in the location of outer inlet, in the out inlet. It's not in the area of inlet. So that's why we'll get negative, but the magnitude is the same. So we have to find out the power work in. It's just simple as derivation by work in times by mass flow rate in. So we know that the mass flow rate in will be 4.263. Thus we'll get the power in. You need to neglect the negative in here. So power in will be 148.8234 kilowatt. So that's all for this question. Thank you for watching and have a nice day. Bye bye.